This conference will now be recorded.
All right, perfect. So hi everybody, and this is the first meeting for December, and for today we're going to focus on workstream number 2, which is the data center PTP profile. Michel from Facebook, my colleague, is leading this workstream, and he would like to present the progress and also the work that is still up ahead for us with regards to this work stream. And we'll dedicate most of the call today to this subject. If no further questions, Michel, I'll hand it over to you.
Yeah, thanks, Elad. Hi, everyone. So like Elad said, today what we'd like to do is go through the data center PTP profile document that we think now is in a state where it is ready for review by the community. I know some of you maybe on the call. I know Alon, there was Greg Armstrong, Hisham, so individuals that have participated in previous calls that have expressed interest in reviewing and contributing to the document. So I think this is all coming together now and timely. So again, what I'd like to go through is take maybe half an hour, 45 minutes to go through this document. There's going to be a lot of information that I'm going to be throwing out. That's okay. And then anyone that is on the call that has interest in participating, at the end of this call, we're going to have a discussion on how do we want to arrange this from a logistics point of view. And just to give you a heads up, perhaps one of the proposal would be to create let's say a breakout work stream from the current a Wednesday meeting that we have at 11 a.m. Pacific, and maybe create a much more focused work stream with a couple of calls in the next couple of weeks to really go through in a lot more details that are contained in that PTP profile. But also for those that want to review and contribute, to start having a discussion, reviewing and doing any kind of resolution on comments that the community is going to bring into this work stream. So why don't we start? I'm going to be scrolling through a document that has about 25 pages with a bunch of sections in it. If there are any questions, please don't hesitate. I think you've probably seen a very, very early draft of that document, maybe, I don't know, maybe about a month and a half ago, maybe 2 months ago. Now there's a lot more information in it, that is ready for review. So obviously, table of contents, we're going to go through all of these, sections, especially section 7, which is the PTP profile itself, and all of the various, sections and attributes that, are deemed necessary or not necessary, for this use case. Okay, let me scroll down. So this is just seems to be like a boilerplate text that was already in the OCP template document, those 2 first sections. So I'm going to skip this. So section 1, I think the scope and overview, I think we've discussed this, a couple of times, and there's been couple of presentations by other community members on the subject of time-sensitive applications within a data center environment. And here, the idea or what's being specified in this document is to develop a PTP profile specifically for that use case. Second thing that you're going to see in this document is, and this is the the third sentence in the scope, is, and I'm just going to read it out. When applicable, the profile also references and reuses information from other PTP profiles or other industry specifications. This is very important because there are, other bodies like the ITU, the IEEE, that have done phenomenal work in the past, 5, 10, 15 years. And it's very important to, reference and borrow and reuse, the information that, belongs in some of these specifications or other PTP profile, right? As opposed to reinventing everything. So when it's necessary, referencing the proper specs and reusing that information, you'll see is within the scope of that the data center PTP profile. Overview, I think, again, this is just very high level wording about what we're trying to do here, and again, that we're trying to develop that PTP profile for the purpose of using this within a data center environment, and that is applicable to various timing appliances. A timing appliance, for instance, could be a piece of software, could be a NIC card, could be a timing card, could be a network element, right? So this is the definition, a high-level definition of a timing appliance. In terms of terminology, section 2, we put a note there because we've discussed that in the past, that says 1588 uses this terminology of master and slave, and it's very important to be inclusive on the terminology of things. And we know that 1588 committee is starting to launch a project to recommend new terminology. However, the terminology has not been fully fleshed out yet, and it's not readily available for us to consume. But we've made great effort in this document to really minimize the use of these terms. Section 3 is just a reference and a copy of the definition of what a PTP profile is. So I'm not going to spend too much time on this, but essentially, if you look at the second paragraph, PTP profile is a set of requirement options, prohibited options, the range and default values, blah blah, for a multiple various functions that are defined within 1588. Then there's a section 4, which is an interesting section, which is additional topics beyond PTP. So PTP does not cover everything. For instance, I give you an example, holdover. If someone wants to specify holdover, well, you can't go in 1588 and find how holdover is being specified. You might find pieces of it, but it's not the full story. So things like, for instance, if you want to classify PTP packets across a packet network, right? You want to give them various different levels of services using diffserv code points, for instance. That's not something that is defined in 1588, but can be defined in the document in that specification that we're going through right now. Section 5. So section 5 is really about framing, the reference model, or the context around, the reference model that's going to, dictate a bit how do we, specify all of these PTP attributes and anything that is outside the scope of PTP. So here, what we go through is to present two models, namely Model 1 and Model 2. Model 1 is what we call the transparent clock model, and Model 2 is what we call the transparent clock plus boundary clock model. So in section 5.1, we put very high level characteristics of what that first model is. So let me just walk you through a couple of them. This Model 1 consists of grandmasters, transparent clocks, and ordinary clocks throughout the model. The grandmaster has a one single network physical port that distributes time. And in addition, the grandmaster that is defined in this profile is what we call a master only ordinary clock. That means a grandmaster cannot be, in 1588 term, a slave only. And this is where we make one reference there for master only and slave only, for instance. And then it becomes clear that a GM is always a GM and an ordinary clock is always an ordinary clock. A GM distributes time and an ordinary clock, receives and processes, time from the packet network. The transparent clocks can have, multiple physical ports compared to the GM and OC that have a single physical and a single, what we call PTP port. The TC can have multiple physical and multiple PTP ports. The physical ports speed, for instance, are 40 gig or 100 gig or higher. All of the links are optical fibers. As part of that model, it's assumed that hardware timestamping done at the physical layer is enabled on all of the PTP capable ports. That the OC will communicate with the grandmaster based on the PTP unicast discovery and unicast negotiation. I'll go into a lot of details on all of these a little bit later in the document. These are just some of the characteristics of Model 1. The communication will be via IPv6 because in the data center IPv6 is used throughout. The end-to-end delay mechanism is going to be used. And not the peer-to-peer delay mechanism. So, anyways, I'm going to cut to the chase here so that we can go through many other sections. There's also, for instance, if you look at this figure that you see right now, this is a very high-level, representation, and I think we've presented that. Some time ago, 3 layers. One is the time reference layer, and this document describes a bit what that layer is, right? So this is where you have, for instance, your antenna system, your time reference, such as your GNSS equipment, and then or the equivalent of what we call a PRT, or what ITU calls a PRTC for a primary reference time clock, and you've got the GM functionality and devices. Then you've got that network fabric layer, which is basically the network fabric of the data center, which are network elements that all or some of them are implement are PTP aware. In this case here in Model 1, all of these nodes that are PTP capable are transparent clocks. There is no boundary clock in this model. And then you've got the bottom layer, which is that server layer, which consists of a very, very large number of ordinary clocks that are attached to that network fabric layer and those transparent clocks. So,
Michel?
Yes?
I have a quick question. Do we avoid on purpose the boundary clock definition in this profile, or it's a future provision that we will add?
Yeah, very good question. I'll get to that answer this in a minute. Thank you. So very high level. This is a bit what Model 1 looks like, and I'll let those that want to start working on the review of this document to really go through some of these characteristics, and contribute to those. To answer your question, Elan, Model 2. Model 2 is shown in Figure 2. Model 2 is where, for instance, we've got the same model, except that the last network element into that fabric is a boundary clock. For the purpose, for example, of scalability. Okay, which I think we've discussed in the past in some of those calls. That's a bit different, but right now, we've put this a placeholder into the PTP profile, and we've just put it as this model is for future definition, so that we can really focus on the model one and all of its details. Okay, but there is a placeholder Elad there. Section 6, we go through it. You're welcome. We go through additional requirements where we, specify that the PTP clocks are going to be IPv6 encapsulation or mapping, that the communication is going to be unicast, that there is no multicast or broadcast communication here. We go through putting out some requirements on, between various ordinary clocks. For instance, like we give a number of plus or minus 5 microseconds. This has been discussed in the past. That this is a requirement that we strive or want to achieve, within this data center PTP profile. Then we drill down into the maximum time error between two OCs, between a GM and an OC. We also talk about the maximum time error between two GMs, two active GMs. For instance, that must be within plus or minus 100 nanoseconds. And our reasons why we're picking these numbers, I'll get into this a little bit later as to why, for instance, it's 100 nanoseconds. And for instance, we put also a maximum time error generated by a TC that also, is within plus or minus 100 nanoseconds peak to peak. Then section 7, this is where we start the definition of the PTP profile. Essentially, we're following the guidelines that are set in 1588 2019 about how do you construct a PTP profile, what needs to be specified in the PTP profile, and also what needs to be specified outside the PTP profile. So section 7.1 is you'll find this. This is pretty standard. There's nothing new here. This is if you open any PTP profile that exists in the industry, you'll find that there is a profile name, a profile number, profile version, profile identifier, an organization name, the organization that is developing or defining that PTP profile. And then source identification is generally a link where you can click on or you can copy and paste, and you'll find a URL that brings you to that specification. So one thing here that we put a note here is, as part of defining these the information for a profile, there is an attribute that is called the profile identifier, which consists of an OUI or a company ID, right? So a unique, essentially, identifier or company ID identifier that generally you get from the IEEE registration authority. So this is something we'll need to discuss with the OCP team to better understand, how OCP is going to get, if they have and if they don't have access to that kind of company ID, how they're going to procure that company ID so that we can put it in the PTP profile. Section 7.2 is basically a clock type, so the GM, the BC, the TC, and the OC, the BC being the future based on what I mentioned previously. I make a reference, for instance, that the GM, for instance, could be, what is being developed as part of a workstream number 1, Elad? Is that correct?
Absolutely, yeah.
Yeah. So as part of a workstream number 1, which is this open source Grandmaster, that could be an instance of a GM. Section 7.3 are the messages that are permitted as part of that profile. So the typical announcing, follow up, if you use a two-step delay request, delay response, obviously. signaling, right? Signaling because we use unicast. And don't forget, for those that are not too familiar with PTP profiles, most of the profiles in the industry, whether you look at the automotive, power profile, and some of the telecom, they're all multicast, except that there are one, two within the telecom or ITU that are also unicast. And that's the reason why signaling message is necessary here. And PTP management, so the PMC or the PTP management client messages are also permitted here. The transport mechanism, section 7.4 says that the required transport mechanism is IPv6 per Annex D of 1588. Nothing really, new here. And it's permitted to use IPv4 per Annex A. May be required in certain instances, but definitely the stuff has to work with IPv6. That's necessary. Section 7.5, the clock identity. Essentially, for those of you that are familiar with the PTP, or maybe those that are not familiar also, so each PTP clock has an identity, a unique identifier that we call the clock identity, which is basically a string of digits put together to form that unique identifier. And there are rules on how you create that uniqueness. And this is what we describe here. But what has been noticed is that 1588 2008, for instance, uses these octets, FFFE, between the third and the fourth octet of a MAC address to create that clock ID. This has been deprecated in 1588 2019. So anytime you see on a wire a clock ID that has this FFFE between the third and fourth, is compliant with 2018, but not compliant with 2019. So, 1588 2019 says that instead of putting FFFE between the third and fourth octet, now you just have to append those two octets at the end of the, the 6 octet MAC address. Okay. Yeah. So again, to create that uniqueness in the clock identity attribute. Section 7.6, we basically say that the path delay measurement mechanism is going to be the end-to-end one, the delay request response mechanism, and not the peer-to-peer. So, and why we specify these things is, for instance, if you look at the Linux BTP as an example, which implements a lot of these, a lot of these features, then you can start mapping what the PTP profile states to what an implementation, might look like. 7.7 class as a service. So again, because in Model 1, for instance, we don't have boundary clocks throughout all of the network elements, now it means that the PTP messages need to be forwarded by the fabric layer. That means that the PTP messages are at the mercy of the routing layer, right? Because the PTP messages don't have a scope of being point-to-point between two network elements. So in that case, there is a recommendation here that in order to minimize any kind of latency and delay variation for these PTP messages that go across multiple transparent clocks, they should be, prioritized to the highest level, of class of service possible, that the operator of the data center, can do. So here we refer, for instance, to the IPv6 traffic class. Elad, I think, is it possible for you to go on mute? Thank you. Yeah, thanks. Section 7.8, profile isolation and domain number. There's a new parameter in 1588 2019 that is called the SDO ID, which generally, if you are an SDO like ITU, IEEE, OCP also fits into that category, that you can request another ID that basically allows you, if you have the intention as an organization to develop multiple profiles, and to make sure that they are isolated from any other profile that other organizations in various industries might be developing. Essentially, you're trying to de-risk any kind of conflict when an operator or someone that uses PTP within its network to have contention between PTP packets that belong to two different profiles. I'm not familiar, or I've never really heard about for the data center that there would be multiple profiles within a data center that would necessitate that SDO ID. Thus, the reason why we say here that this PTP profile does not require an SDO ID, since it will only be the profile in operation within the data center. And that if OCP, for instance, we decide to create multiple profiles in the future, that we could still perform isolation via different domain numbers. So we have different ways of doing profile isolation. So anyways, I'll let people review that and comment on this. So section 7.9, one-step and two-step operation. The profile clearly states that, for instance, a GM must support both one-step and two-step operation on transmit, or can support both on transmit. So a GM is free to, someone that designs a GM, to say my GM is one step only. That's fine. My GM is two step only. That's fine. My GM can do both on transmit. That's also fine. In the case of a transparent clock, we define that the transparent clock must support one-step operation on transmit, on egress, and may support two-step operation. And we say may support here because section 7.10 gives an example of why TCs in two-step operation might be challenging for a data center environment. I'll get to that in a minute or two. And then we say that, so on receive, all PTP clocks, whether you're a GM, a TC, or an OC, must support both one-step and two-step. I mean, on receive, you've got to support both, right? So if you receive a sync, you process it for one step. If you receive sync plus a follow-up, you got to process it on receive. But on transmit, it's different, right? You can support one or the other. Okay, we talk about, yeah.
I suggest we pause for a second and check if there's any questions.
Yeah.
So guys
Okay.
on the call, any comments so far? I think we're good.
All right. So yeah, we talk about how do you use the flag to differentiate whether you're a one step or two step. So here it's clearly explained. Section 7.10, this is where the transparent clocks are going to be one-step operation, but it's possible to use a two-step operation. We explain we explain a bit, the two-step operation in TC, which is a very funny implementation, right? For those of you that are familiar, you know that in the two-step TC, not the GM or OC, but a TC, you've got to keep state information because the residence time that you generally you would want to write into the delay request now has to be kept as state information and has to be correlated with the corresponding delay response message that comes back in the other direction. A little bit convoluted in my opinion. But that's how the mechanics of a two-step DC works. And that means that if for whatever reason the delay requests are not passing through the same transparent clock that calculated the residence time, you're going to have a mess, a big mess. And it can happen in the data center because of the the scalability of the network fabric, that you have multiple network elements, and each multiple network elements might have multiple links, which means that you might have multiple paths between a grandmaster and an OC. And it could happen that the property of making sure that a delay request and a delay response, which flow in two different directions, go through the same transparent clock might not always hold true when you use these, give examples, these packet spraying type of technique, load balancing, ECNP type of techniques, and so on. So that's the reason why the one step is obviously preferable. But if someone wants to use a two-step, it's also possible, but you have to be careful about this this assumption that all of the packets flow through the same links in the same transparent clocks. All right. I hope.
Have you thought about using segment routing within the data center so that you can specify a specific route for BTP messages?
So I think every data center operator has various ways to achieve the different communication paths, and segment routing is one of them. Yes, that can be used. So here from this is a good question, Hisham. So irrespective of how, for instance, the routing is done in the data center, assuming in model 1 we have a set of transparent clocks. If you use a one-step transparent clock, then you want essentially you won't end up into the situation where the delay request and the delay response, or the residence time essentially will always be added to the delay request, and that there is no dependency on what happens to the delay response, whether it's coming through the same path or another path. I hope that was clear. I'm not too sure, but yeah. I think from BTP point of view, that's how I think is important to look at it, Isham. But please go through that, those sections, and if you have any comments, like I said at the beginning of the call, we can certainly discuss those in greater details.
The document will be available on the wiki.
Yeah. I'll talk about this, how we're going to do this right after I'm done going through the document. Yeah. Section 7.11. We talked about the PTP message rate. I'm going to go a little bit quicker because it's already 11:37, and I'm about halfway through the document, which basically places bounds on the different message rate. And there's nothing really new here, except to say that a GM must support the full range, and an OC might support a subset of that range. So we make it quite relaxed. PTP inter-message interval. So there are requirements, if you are, for instance, designing a grandmaster, there are requirements that are important to meet when it comes to the intermessage intervals for the various messages, the unicast messages that are being transmitted by a GM. So there are two actually primary requirements. One is to maintain an average over a given number of samples, and the other one is to look at the distribution of these messages that need to fit within the certain bounds. So we explained that here in this profile. There's nothing new, by the way, here. All of this is already within 1588, but here it's a lot more, I think, concise as to what is necessary. 7.13 is unicast communication. So we know in unicast communication there are two main features. One is unicast discovery and one is unicast negotiation. Unicast discovery is about how do you make sure that, for instance, an ordinary clock, imagine you've got tens of thousands, hundreds of thousands of them, are capable of finding the grandmasters that are part of a network. That's what unicast discovery allows you to do. Essentially, it allows you to provision those ordinary clocks with a set of, let's say, IPv6 IP addresses that say, here are, the list. Here's the list of grandmasters or GMs that you have, at your for you to negotiate with, to basically pick one as, an active GM, or use others as standby GMs in case there is a failure of the active one. So the unicast discovery does that. The unicast negotiation says that once you've discovered the grandmaster, then you want to request service from those grandmasters. You want to request unicast service. And what are those services? You want to request announce message, sync message, and you want to request for a delay response message. So there is a protocol that allows you to negotiate that. And what do you negotiate for? Well, you negotiate for the duration of that unicast session you want to establish with the grandmaster. You negotiate, for instance, for the rate of the messages that the ordinary clock might want to ask for the GM. Okay, so this is all defined in unicast negotiation in the section 16.1 of 1588. But here we, put a little bit of text to really explain, because it's not that trivial when you read 1588 on how all of this works. So here we explain a bit how those two features, both the unicast discovery as well as the unicast negotiation work. And again, what I said is, for instance, these are 4 parameters that exist in the in 1588 for that I've highlighted here, that you can start making a mapping or correspondence to what is, for instance, in an implementation like Linux TTP, okay, that use some, or that I've renamed some of these parameters. Okay, here we go. For instance, we also explain how you might want to provision those various GMs and ordinary clocks. So picture this. Imagine you've got a very large number of ordinary clocks that the total number of ordinary clocks in terms of what they request from a grandmaster would just overload one grandmaster. That means you need to deploy multiple grandmasters. 1588 is a little bit silent on that, on how many grandmasters, generally there's one, but here, because we use unicast, there are ways now to have multiple active grandmasters and, for instance, multiple standby GMs in case there are failures. So we go through some explanation about how one would want to group those ordinary clocks. So group them into larger groups. And these larger groups are assigned to, for instance, one active GM and perhaps multiple standby GMs. So it allows you to really organize a bit your, your redundancy within the data center. So we go through a lot of explanation on that. And then we also give another example where you might have multiple active ones, but maybe less number of standby. So you can tolerate failures, but you cannot tolerate, all failures of all active GMs, right? So these are trade-offs that one has to do, okay? And here there's nothing that is, mandatory or normative here. It's, these are examples, right? It's left to the, to the operator of the data center to really figure that out. Then we go into the unicast negotiation. For those that are familiar, this is very straightforward. It consists of a bunch of TLVs, like the request unicast transmission, the grant, the cancel, and the acknowledge cancel. We synthesize a bit what is written in in 1588 on how the mechanics of that negotiation protocol works. For instance, maybe a figure will help. And this is where you have, for instance, the signaling messages that are requesting the service for announce. Then the GM starts to send those announce. Those announce are sent with an inter-message period, of what was negotiated. Negotiated means what was requested and what was actually granted, right, by the grandmaster. The grandmaster does not need to grant whatever the OC is actually requesting, right? There can be a bit of intelligence to say, no, maybe I'll give you a lesser number of message rate, for instance. And then there's a duration field, right, that says after X seconds, minutes, or days, the OC has to request again. It's like a keep alive service. Okay. And then there's the BMCA, right? So the BMCA is probably one of the most important thing of the PTP protocol itself. It's not always discussed. That's why here, we go through a bit of text to explain that this profile is based on the default BMCA, but we can also base it on what we call, for those that are familiar with the 8275.2, which is one of the telecom profile that uses, by the way, unicast. They have defined an alternate BMCA, and we're basically saying that for model 1, it does not matter whether you use the default BMCA or G8275.2 alternate BMCA, they will result in the same behavior for model 1. Now for model 2, that would be different, but for model 1, because this, what we call the steps remove attribute is equal to 1, in both cases, both BMCA default, to the same result. So what does that mean? It means that, for instance, if you look at Linux BTP, you could say, I'm going to use whatever exists in 8275.2, to implement the BMCA, or one could say, I'm going to resort to using the default BMCA.
Michel, do you plan to support multiple domains?
No, this is a single domain here.
Okay. So no requirement for multiple domains.
There is no requirement to have multiple domains. I can't think of a reason why you would want to have multiple domains. Like I say, this active standby is one of them. You could say the different active GMs are in different domains, but you don't need to do that. They can all be in the same domain. They are just differentiated by what we call the priority 2 attribute in the BMCA. So how you, and this is what other profiles, tend to do. They use the priority to give a priority to which GM, for instance, is active and which might be standby. Essentially, which is better than, you know, another one. And if the better fails, then the next better takes over. Okay, so as opposed to try and segment this using different domain numbers. But I know it was talked about 12 years ago in the first one of the first telecom profile to use multiple domain numbers. Yeah, I hope I answered your question.
Yeah.
Yeah. Okay. Then in the case of the BMCA, we and I don't want to spend too much time on this, but we will certainly do that, you know, in the next coming weeks. We put values to the most important, you know, data set parameters, like for instance, the clock class. We see really 3 clock class being used: 6, 7, and 52. 6, you're traceable to a primary reference source. 7, you're not traceable anymore, but you're in holdover, and you have very good holdover. And 52, you're still in holdover, but you're totally lost, for instance, or like you're in free run, right? So that's why, you know, we've got 6, 7, and 52. And this is very similar to also profiles like 75.2, 8575.2, 8275.2, you know, from ITU that uses, yeah, you know, unicast. Clock accuracy, scale log variance. And here I make again what I said, reuse. This clock accuracy, we say it's going to have X value 21. If you look in 1588, it says that the accuracy of the GM is going to be, you know, within 100 nanoseconds, and that's why we, you know, we use this value, and we make a reference in the text to 8272, which is PRTC-A defined by ITU, because we don't think that those grandmasters or those PRTCs are going to be, you know, different than what is used in, you know, in telecom. I mean, if you can reuse and it gives you 100 nanosecond, that's probably, you know, good enough for what we're, you know, looking at right now. So yeah, so we go through, you know, those attributes in a table format. Then the last section is the network limits. There's been a lot of discussions about how do we budget for all of that. There's nothing scientific here. This is an initial analysis. For those of you that really want to go through this, please go through this. We go through the various effects that we think contribute to the time error at an ordinary clock. And again, you know, the requirements that we put here is that any two OCs must be within plus or minus 5 microseconds of each other. So imagine you have a very, very large number of OCs within a data center. If you would measure any two of them at a particular incident point, they need to be within plus or minus 5 nanoseconds, which means that you can meet this if you look at an OC relative to a reference like TIE, right, which is available at the Grandmaster, to be less than 2.5. So if you meet the first requirement, you obviously satisfy the second one. That's what I'm saying here. So we go through the different effects here. We talk about the timestamping granularity, and you know, a lot of these things are already well known in various standards, right? And have been you know, discussed you know, quite a lot. There's really nothing new here. Timestamp generation, which has to do with that measurement plane error. If you have a TC, then you have an error that is basically the, you know, due to the resident, an error on the residence time that is due to the free run accuracy of the TC, and you know, the residence time itself. Then there's the noise generation of the OC oscillator, which is dependent on the oscillator and the PLL characteristics. The GM accuracy, which again we use 100 nanosecond, and we refer to PRTCA of ITU. There's a constant time error, which has to do with any kind of a link and node asymmetry, even after you've compensated for, right? That you might want to budget for. And then there's an error within the application itself, right? So we've heard the other day from Kevin and from my colleague Ahmad and Lotan that, for instance, like when you go through the Linux kernel, when you go through PCI and so on, that there might be errors there that you might want to budget for.
Michel?
Okay. Yes.
I'm monitoring the time, and we're about 5 minutes left of the hour.
Yes.
So
okay.
I hate to stop this. This has been. Thank you for sharing all this work and findings and suggestions with us. I would like to ask you, what do you view as the next steps, and what is the kind of help that you would like from the community? Yeah. So the last section was exactly this one that I'm going through, which is the budget. Yeah. Okay. And then obviously the references, and that's it. So in order to address the question that I think Hisham had and Elad, you also had, what we're going to do now is we're going to post this document on the wiki that is ready for review. We're also going to put it on GitHub for those that prefer to perhaps make comments on review it through Git. And then, Elad, what we need to discuss, and we can do that, with the mailing list, is I think this is a proposal. We set up a parallel work stream that says in 2 weeks, or give the community a bit of time to digest this document, maybe prepare some comments, and then we do a couple of perhaps breakout sessions for those that want to participate into the review and the resolution of some of these comments. And I know guys like Alon has expressed interest, Greg, Hisham, and so on, and whoever else, would be very happy to work with all of you guys, or all of you, on this. Sounds good. Sounds good. I think it's a great approach. So if you guys are looking for the link for the wiki, then you can Google Open Compute and tap, and it will be the first thing that comes up to you. I'll paste the link here. Yeah. Okay. So we'll post. We'll basically submit that document as you see it now for review. People can download it, and then Elad, do you think through the mailing list we can propose perhaps a couple of time slots? And yeah, I can reach out to those that have already reached out to me, Alon, Greg, Hisham. I've got their email, and I can say, guys, let's pony up together, and let's figure out the time where we want to go through this. If that's okay with the, with the community members, and anyone that is on the call also, if you have interest or some of your colleagues have, they can reach out to me or to Elad or through the mailing list. Sounds good. We will start with the list of volunteers we have for this work stream, and we'll keep the mailing, the entire distribution list on copy for if anyone else wants to join at any point. But sounds like we have a core team to start with and take this forward. So thank you very much for the initial volunteers, and of course, Michel, for leading this.
Thanks, Michel.
I just wanted to ask about the. I wanted to ask about the time error section. Do you plan to have it as a detailed time analysis, or should that be a subject for a different project, for a different stream?
That's a very good question. We can definitely discuss that. If you ask my opinion, I would say that this is probably performance related and maybe needs its own kind of work stream. Because I know where these analysis, and you probably know where they can go, simulations and all of that. And they're probably very important. We can ask the community, and if they are, then maybe there's a sub work stream on that.
I tend to agree.
Okay.
We've been
Thank
playing around,
Yeah.
we've been tossing around this idea if we will need a work stream for the oscillator hardware component side of this equation, and how to steer it forward. Any ideas here, Nazar, are welcome.
Yes.
And that's something I could probably help with, as much as I can. I'm not a networking expert, but we focus on timing. So I think we could share some ideas about timing and where we can start.
Absolutely. And you know, I would not be surprised if some of this kind of work could end up into the PTP profile, because that's not just a PTP profile. We can specify things that are outside PTP also if we want in a document like this, right? Yeah.
Mm-hmm.
What we want to make sure, I think, is that there is a document that provides information to the community about how you start implementing things, how you start deploying, and how you start building things, right? Yeah.
Okay,
So if you're interested, we'll add you to the loop. Yeah.
Yes, please. I will try to help. I do not know a lot about networking protocols, but I'm knowledgeable about timing, so that's the portion I can help with.
Thank you.
Fantastic.
Appreciate it.
Thank you.
Okay, we're exactly on time. Are there other comments or questions from the team? Not. I will thank again to Michelle and all the feedback we got today. We'll close it off and see you again in 2 weeks' time.
And thanks, everyone.
Thank you.
Thank you.
Thank you.